Visualizing your experimental data is a very important skill, and it's a task that you need to do almost every time you take experimental data. At the very least, you're going to be able to find a visual cue or descriptive way of describing the relationship between them. You might say, oh, they're linear, they're nonlinear, proportional, random, oscillatory, whatever. You're going to find that. But if you're lucky and you find that your data fits a form that's reasonable, let's say linear, then there's an equation that all lines follow, y equals mx plus b. So if we graph our data, we can find this equation, and that finds a definite relationship between the data points that we just measured. So with a linear relationship, just to remind you what the pieces are, y is just the variable that's on our y-axis, x is on our x-axis. That's obvious, and we'll get more detail about those in a second. But the key thing is the slope is something that you've seen before, but is often forgotten. Some people call it the rise over the run. The change in y over the change in x is great. Right here is a way to calculate it. If I take any two data points, x1 and y1, and x2 and y2, here's how I can calculate that slope. We'll use this technique later. And finally, b is the y-intercept. It's the one that most people don't recall what it really means. It means it's what's the value of y when x is equal to 0? Where will the straight line intercept y when x is equal to 0? We can solve for it once we've obtained our slope just by rearranging our equation for the line and then plugging in a value for y and x, and knowing our m, we can just calculate it. It's pretty simple. So let's imagine we've got some sample data. Just something we have a machine that produces a length of some material, and what we do is we then go ahead and measure the mass of that material. A simple experiment. It's not really all that interesting, but it'll do the point of us learning how to make the graph. So first off, the independent variable is the thing that we control. In this case, we controlled how long the object was. So because we control that, it's independent of any other variable, and it's the x-axis, the horizontal axis. The other variable, the mass, we measure that after we've cut this to a particular length. Therefore, it depends on the length we choose, and it will become our y-axis and is our dependent variable. Here's the data that we got from doing the experiment over and over. 5 trials, as a matter of fact. We'll keep track of this the entire time, and we'll use this particular data. All right, so here's what we need to do. We need to define how we're going to present our graph in the lab notebook. We're going to see how it's oriented. We're going to learn how to scale our axis so that our data fits on there properly. We want to use a graph that uses all the space and is as accurate as possible. We want to plot the data points. That's the simple part. Then we're going to draw the best fit line, which is often a question that students have. How do I do that? Determine the slope of that line, determine the intercept, and then finally write that relationship down using the variables that match our measured stuff, not x's and y's. So it starts by finding out the orientation. And there's 2 possibilities for us, often called portrait and landscape. However, for us, we've decided that our mass is going to be our y-axis and length our x. So we've got this as our 2 options. So let's look at our data. And if we look at our data, we can see that our length, it ranges from 6 to 29. That's a difference of about, let's say 25, just as to get an idea. And here our mass, it has a range of 16 to about 28. So that's a difference of about 12. Well, the larger difference right here of 25 should go on the larger edge. So our length needs to be on the longest edge of the paper to make this graph as accurate as possible. Therefore, we're going to choose the landscape version for this particular set of data. That's what we'll use. With that in hand, we now need to scale the axes, each of them, so that we get the most efficient use of space and the most accurate results from everything else we do with our graph data. So don't forget that when we make our axes and we draw them, we want to leave room for axes labels left of our y-axis and below our x-axis, and even some more room below our x-axis because we're going to put a figure caption below that. So we need to leave a little bit of room for that. Here's our data once again, just to remind you. And here's a possible set of lines for the x-axis. So you may have 20, you might have 25, you might have 30, you might have 33 of these little lines along the bottom of your axes. I'm going to number these from 1 to 25 in my head. So here's number 10, here's number 20. I wouldn't write this on my graph, but now I know how many there are. There's 25 across the bottom. So I'm going to be talking about my length data because that's what's going to go along this bottom x-axis, the horizontal axis. And one thing I could do is I could just immediately scale this from 0 to 25. However, that doesn't fit my data because my data has 2 data points that are larger than 25. So really what I want is I want my data to go to at least 30 on the right-hand side. So I could go from 0 to 30. That seems like it's all solved and easy to handle. However, that makes each one of these divisions 1.2. That's 30 divided by 25. And that's pretty hard to handle because now I have a hard time estimating anything in between. If I want to estimate in between here, this is 1.2 and 2.4. So that's not as easy as if this was 1 and 2 or 0.1 and 0.2. So I could then take a look at my data and say, you know what? I'm going to round up the largest value to 30, round down my lowest value to 5. And now I've got something that ranges from 5 to 30. And if I do 5 to 30, I notice that that's a difference of 25. And then each one of these becomes a division of 1. I can do this no matter what my scale, what my data is. I can adjust it so that it fits on there to the best of its ability. I may not get to use all of them. There may be 3 more on here. There may be 28 lines that I could have used. But I'm going to stick with 25 because it's a nice number that fits my data. So it takes a little bit of skill and practice, but as long as you follow the rules of trying to round down your lowest, round up your highest, making sure everything fits on there, you should be okay. With that in mind, you should probably think, what would you put and what kind of scale would you use for the mass? We've decided to use 5 to 30 for the length, but what would you use for the mass? So I'm hoping that you're all looking at this and saying, I'd round this up to 30, round this down to 15, and the difference would be 15 to 30, so I'd have to have at least 15 of these divisions to make it work out and be very easy to use. As a matter of fact, that's what I did when I made the graph. So now that I've made those decisions, 15 to 30 on my y-axis for my mass, 5 all the way up to 30 for my length, I can now plot the data points. As you see, I put them on there, in this case, as little triangles, or little diamonds, I'm sorry. You could use circles or dots. It's best not to use X's, but very clearly you can see that our data is increasing and pretty linear. It's not perfect, but it's pretty much a linear relationship. So let's investigate and get the exact details of that relationship right now. Because our next step is to draw the best fit line. The challenge here is that best fit lines have to match both the trend that we see. In that case, in this particular case, as the length increases, the mass increases. But it also has to give the relative slope of those so that they land through the intercept properly. So let's take a look at a possibility. This is a possible line. And I have to say that the slope of this line really matches the data quite well. However, the person who drew it chose that these 2 data points to go through, which means for some reason they're almost saying, I don't trust these other 3. The other 3 say that the numbers should be lower, while these say the numbers should be higher. So this one right here, while it has the same slope, or the proper slope it appears, I think it's going to give us too large of a y-intercept, because as this extends down and finally crosses at 0, I think it's going to be too high. A similar result would be if we chose to these lower values from the trend we see, and sadly this one right here kind of ignores the middle two that we had before that we thought were so important. We need something that's kind of in between there. So I might try to tilt a little bit, and when I do this, I get a pretty good response to the first three, but now these other two at the very end, they're no longer really considered, and they're not close to the line. Our goal is to get all of these close to the line, and possibly none of them on the line. So when I get done, I think that this one right here is probably the best result I can get. I'm going to let the computer create a result on the next slide, but this is me just drawing one on here, and as you can see, it doesn't really go through any points. It's pretty close to this end point, but it's close to all of them, but not right on. It's got the right slope, and it's probably the best measurement, best representation of what the data is doing. So here's the final result done by the computer, and you see when the computer does it, it actually takes it right through this last data point, so that's pretty nice. The question is, how do we compute the slope now that we've got the best fit line? First and foremost, we use the line itself, not the data points. That means this data point is not something I'm going to use as one of my y2, x2 values. I'm not going to do that. Instead, I'm going to use points on my line, because I've now said the line represents the best, and it takes into account that I have errors associated with these measurements. So what I'm going to do is choose some data points on here that cross the grid lines. I've got these grid lines. So if I choose a few data points, I can find two here that look like we cross right where the grid lines cross. So I know where those are. This one is at 28 and 27. This one right here is at 22 and 17. Now, I've chosen this other one just to show you that this is about halfway between 18 and 19, so I can estimate this one is 18.5 pretty good. This one also looks like it's pretty close to halfway between. It's hard to say. So you're still guessing a little bit, but your guesses are more accurate when you can do it in that fashion. So what I'm going to do is, because this one's guessing, even though I can get the value and say that I think it's at 9 and 18.5, and this one's at 17 and 22, and 28 and 27, what I'm going to do is I'm actually going to just use the other two that I think are going right through the cross of the grid lines. With that said, I can find my slope by looking at my slope equation, plugging in the values from the two data points, and doing the math. Now, I need to realize a couple things. First off, my Y data have units of kilograms, and my X data have units of meters, and I need to incorporate those into my slope. When I get done, I have 3 digits up here that all end 1 decimal place. So I end up with an answer that should be only 2 decimal places, or 2 significant digits. So while I get 0.454 with my calculator, my real answer is going to be 0.45 kilograms per meter. So make sure that you can follow the significant digits that just went on right there. With this value in hand, I can now find the intercept by rearranging the equation for a line, b is equal to y minus mx, choosing any data point I want. I think this is the most accurate one, so I'm going to choose this guy right here, the 28-27 data point. I think that's the most accurate crossing of what the grid lines, and I'm just going to plug those in along with my slope. Notice I've brought along an extra digit with my slope to reduce round-off error. When I'm done, I get 14.288 with my calculator, but I must realize that this number right here will have 2 digits, and this one will have 3, but it ends at the first decimal. So I have to end my answer at the first decimal, and my intercept becomes 14.3 kilograms. So how do I wrap this up? I find the equation of the line. The equation is not going to have y's and x's in it because my data are mass and length. So what this all says is that my mass is equal to the slope times the length of the board plus 14.3 kilograms, not y is equal to 0.45 times length plus 14.3. We use our actual values from our y and our x. I hope this helps you understand how to make graphs in the lab and how useful they are in finding the relationships between the two variables involved.